Last topic of today's this one, the lambda one, that is our DFA minimization. Okay. So what is DFA minimization? So that we are going to talk about. So let's write DFA minimization. We can also call that we can also call it as a DFA. Can be also called as DFA minimization. The reason being is that so there are certain what you can call certain states which might be redundant. We do not require them, right? And the thing is, we can to then again we have to understand, and then we can remove them, right? So these states are what you can call. Then again, states can be divided into productive and non-productive states. Okay. So what do you mean by the productive state, right? Productive state means when you can call as this one. We just write this is a description. Right. So that productive states will be kind of which directly are involved in what you can call a language recognition subjects. Right. Recognition. Okay. So one such a state can be called what you can call that let us say the initial state, and then there are what you can call as a final state. Okay. Without this, the what you can call the states. 1 second, please. Without this, the states are what you can call they are not required, right? Without this, what you can call the DFA is not productive. Now, when you're talking about the non-productive states, then these are do not uh, have much importance in DFA language recognition. So one such state is what you can call the, as example, dead state. So how to identify the dead state? So then dead state, and generally it's looping, and it does not reach what you can call the final state, right? Anywhere it does not reach the final state. There is no link, and then there is what you can call the unreachable states. So unreachable states are states where there is no path from the initial state to the what you can call to the what you can call unreachable state. Okay, so that is what you can call as a this defined state. So what is the algorithm for this one? So there is again one is concept called. So when DFA minimization, there is a concept called. Again, this is another part that is a distinguishable and indistinguishable states. So the concept is follows in as such. So let us say if I am writing distinguishable state, okay. So distinguishable state is what you can say. One second. So when the states are distinguishable to each other, and distinguishable state means states are not indistinguishable to each other. How to means how to verify this thing? How to verify this thing? So let us remove this one. Delete rows. Okay. So again, when you are saying, let us put this one, the given two states. So let us say so when you're talking about a distinguishable and a non-distinguishable state, so let us take this one, let us take states in here. This is what you can call P. Let us say make it as 0. And let us make this as 1. Okay. So then again, let us say put this as a P and let us put this as a state as a Q, and Q is what you can call as the final state. Okay. Now P on 0, say let us say it goes to Q. Q on 0 also reaches to Q, right? P on 1 reaches to P, and Q on 1 also reaches to P. Okay, so now in here we come in this conjuncture that let us say, let us put this one into this one. Okay, so now, okay, del P, comma, let us say I'm putting 0, and it generates Q, right? And again, the same thing happens. So again, let us put this on del. I'll put this one as del. Q on 0 generates again Q on 2. Okay. So again, if I take this one again, next steps, Q on 0 goes to Q on 1 goes to P, and again Q on 1, sorry, P on 1 goes to again P. So in here you have to understand in this particular, for this particular states, right? In this particular case actually. Now P on in a given input is goes to a final state. Q on in a given same input goes to a final state, right? And again in here, Q on a given input goes to a non-final state. P on given the same input goes to a non-final state. In this case, we can call that P and Q, P and Q are in this in which, okay. So this is the what you can call both. I can writing this one, which is final, which is final. In here it is just a non-final, and in here it also reaches a non-final. Okay. So in this case, we can say the P and Q are indistinguishable to each other, right? And we can combine them into one single step. Now, if I again repeat this thing in here, P on 0 goes to P, and P on 1 goes to Q, right? So again, we see in this case, again, the situation reverses. Situation reverses in which formula? P on 0 goes to final, but Q on 0 goes to a non-final state. This is the non-final, I think. This is non-final. And this is what you can call as a final. This is again P on 1, Q on 1 goes to P, that is a non-final, and this one is what you can call as a final. In this case, we can say that P and Q are distinguishable to each other. In that case, we cannot combine them into one single state, right? So what is the algorithm that can come up from it? Okay, so let us go into these definitions. Okay, what are the types of states? Productive, presence or absence of this states can change the language accepting capability. Non-productive cannot change. Dead state, no path to the final state. Self-proof for all symbols. Multiple dead states. Don't eliminate the dead state. We cannot eliminate the dead state. And there are unreachable state. There is no path from the initial state. Eliminate unreachable state. Then there is distinguishable and indistinguishable states. Now, two states, P and Q in DFA, are said to be indistinguishable if and only if PW, if is in final, it implies Q on W is also is a final state. If again P on W is a non-final state, then del on Q on W means it's a non-final state, right? This is what you can call as a indistinguishable state. And then again, when you cover distinguishable states, so P and Q on F goes to final, it implies Q on W does not go to final state. In that case, P and Q are distinguishable, right? So again, the properties are distinguishability has this one only the what you can call symmetric property, but indistinguishable property has all this property: reflexivity, symmetric, and the most important, transitivity. If P and Q are related, then Q and R are related, then P and R are also related. Okay, is it understood? Okay. Now let us. What is the algorithm for this one? Now I have to minimize the DFA. Now convert the DFA transition into transition table, remove the unreachable states, partition the remaining state into two sets, final set, non-final set. This step is called the zero equivalence. Compute the next equivalence of one equivalence, two equivalence, three equivalence, so on. Check for distinguishing each state. And if states are distinguished, then split it into make one into another state, repeat this step until the states are indistinguishable. Okay, so this is the, okay, let us take an example. Let us take the example. We have to minimize this DFA, right? It's a very big DFA. We have to minimize the DFA. Okay. So what is the first principle? We have to create a table, right? So how many states are there? 1, 2, 3, 4, 5, 6, 7. 7 states are there. Okay, so there will be 1, 2, 3, 4, 5, 6, 7, 8. How many inputs are there? 2 inputs. Okay, we put them all in here. Is it understood, right? Are you all understanding it? Okay. So I'll put the states in here. I'll put inputs in here. Okay. Q0, Q1, Q2, Q3, Q4, Q5, and Q6. Okay, Q0 on A goes to, let us say Q1. Q0 on B goes to Q2. Q1 on A goes to Q1 itself. Q1 on B goes to Q3. Q2 on Q2 on A goes to Q1. Q2 on B goes to Q2 itself. Q3 on A goes to Q1. Q3 on B goes to Q4. Q4 on A, Q4 on A, where it is going to? A should be there, yeah, Q1. Q4 on B, B should be there, A, B goes to Q2. Q5 on A goes to Q3. Q5 on B goes to Q4. Q6 on A goes to Q2. Q6 on B goes to, okay, so Q4 is our, what you can call as the final state. Okay, now tell me which are the unreachable states? Anyone? Which are the unreachable states?
Q6 is one.
Okay, see in here you will never find unreachable states in here, right? You can find Q1, Q2, Q3, Q4, but you see Q5 and Q6 are not in here, so they are unreachable. So I'll just delete them. Okay. So our hub, so already 2 states are reduced, right? Now we have to find the, so distinguishable and indistinguishable states, right? Distinguishable, okay. So we'll find the zero equivalence first. Okay, so we will do now use 2 sets. So we'll write zero equivalence. And under this, whatever we'll do, we'll put this insert equation and we'll put all the states in here, right? Q0, comma, all the non-final ones, Q1, Q2, Q3. right? And again, then there is another state, and the other state is Q4. Okay. Okay, understood this one? Is this okay? Now from zero equivalence, we have to create the one equivalence, right? So zero equivalence, you say we have to find which of these states are indistinguishable, or we can see what are the states that are indistinguishable from each other. See Q0 and Q1. So Q0 on A goes to Q1, okay, and Q1 on A also goes to Q1, okay. So they are following the same set only. Now Q0 on B goes to Q2, and Q1 on B also goes to Q3. So they are all on the same set. So Q0 and Q1 are equivalent, right? Now we can take any of these or any of this, right? Now I'll take Q0. See, if I take Q0 and Q2 equivalence, then it is also equivalent to Q1 also. So if I take Q0 and Q2, let us take Q0 and Q2. Now Q0 on A goes to where? Q1. Q2 on A goes to Q1. Okay. Now Q0 on B also goes to Q2. Q2 on B also goes to Q2. So all are in the same set only. So Q0, Q1, Q2 are equivalent. Now let us say for the Q3. So let us take only one of them, Q2 and Q3. Let us say Q2 on Q3. Q2 on A goes to Q1. Q3 on A goes to Q1. For this A, it is okay, but it is for any number of strings. So we have to also think about B. But we see in here that Q2 on B goes to Q2, but Q3 on B goes to Q4. Now Q4 is a different setting. Now in this case, we have to break this set. So we come across in here one equivalence. So what is this one? So it will be now Q0, Q1, Q2 will be in a different set, and Q3 will be in a different set. This is again one equivalence. Now we will do in the Q0, Q1, Q2 and see that. Now see Q0 on A goes to Q1, Q0 and Q1 on A also goes to Q1. Okay. Q0 on B goes to Q2, and Q1 on B goes to Q3. Now again Q3 is a separate set in here. So again Q0 and Q1 are different from each other. So let us take this for Q2 also again. Q0 and Q2, let us say Q0 and Q1 goes to Q1, that is in the same set. Now Q0 and Q2 goes to Q2, again in the same set. So in this set, Q0, Q2 are equivalent. We have to break this one. So we will now, this state is again broken. So Q1 will be again separated. Okay. So now again let us take for Q0, Q2. So Q0, Q2 again, let us say Q0 and Q2 on A goes to Q1. So Q0 and B goes to again Q2. So they are again in the same set only. So this is again the same set. So now we stop in here. Three equivalence, we stop. We stop in here. So because two equivalence and three equivalence are same to each other. Okay, so now we stop. Okay, understood this one? Is this understood? Now again, if we see, now we have to use this one to create this, we have to minimize this DFA, right? So how many states are there? There will be 4 states only, right? So what are the states? This is Q0, Q2. Q3, and again there will be Control C, Control V, there will be Q4. Okay, now you tell me Q0, Q2 on A goes to Q1. A. Now Q0, Q2 on B goes to Q2 itself, so there will be a loop over in here. So this one will be okay. Now let us say for Q1, Q1 on A goes to Q1, again a loop. Q1 on B goes to Q3. Q3 on A goes to Q1, and Q3 on B goes to Q4. Now is this okay?